What's the deadliest thing in the universe? Black holes? They're cosmic vacuum cleaners, sure, but they're slow. You'd see one coming from millions of miles away. Asteroids? Cute. We have entire government agencies dedicated to tracking rocks that might bonk us on the head. Solar flares? Please. We just talked about those. Inconvenient, but manageable. No, the deadliest thing in the universe is something far worse. Something that makes every other cosmic threat look like a gentle warning tap on the shoulder. It's called a gamma-ray burst, and here's what makes it truly terrifying. It travels at the speed of light, which means the moment you detect it is the same moment it's already killing you. 10 seconds of exposure can sterilize half a galaxy, strip the ozone layer off a planet from 10,000 light-years away, cook every living thing on the surface with radiation so intense it makes nuclear weapons look like birthday candles. And the worst part? There's absolutely nothing we can do about it. No warning system, no defense, no last-minute Bruce Willis heroics, just instant, unavoidable, extinction-level annihilation delivered at 186,000 miles per second. Oh, and there's one pointed directly at Earth right now, a star system called WR104, sitting 8,000 light-years away, aimed at us like a loaded cosmic shotgun. It could have already fired. The gamma rays could be racing toward us right now, crossing the galaxy at light speed. We wouldn't know until 10 seconds before every living thing on Earth starts dying. Sleep tight. This is gamma-ray bursts, the light-speed extinction events we can't see coming. I'm about to explain why this is the most terrifying phenomenon in the universe, why it might have already killed us once, and why there's literally nothing anyone can do to stop it. And yes, we're going to talk about money, because even though a gamma-ray burst would instantly erase $200 trillion in global economic value, the amount we spend researching them is, wait for it, basically zero. Because what's the point of funding research into something that kills you before you can even say, I should have bought that life insurance policy? Let's talk about the universe's instant kill switch. Let me start with a simple question. What happens when a star 50 times more massive than our sun runs out of fuel and collapses into a black hole in less time than it takes you to microwave a burrito? The answer is the most violent explosion in the universe since the Big Bang itself. We call it a gamma-ray burst, or GRB. And when I say violent, I need you to understand the scale we're talking about here. A single gamma-ray burst releases more energy in 10 seconds than our sun will produce in its entire 10 billion-year lifespan. Read that again. More energy in 10 seconds than 10 billion years of sunshine. If that doesn't make your brain hurt, you're not paying attention. Gamma-ray bursts are jets of electromagnetic radiation focused into beams so tight and so powerful that they can punch through entire galaxies like a cosmic laser cutting through tissue paper. When one goes off, it briefly outshines every other star in the universe combined. For a few seconds, a dying star in some random corner of the cosmos becomes the brightest thing in existence. Now here's where it gets fun. These bursts come in two flavors, and both are nightmare fuel. The first type, short-duration GRBs, last less than 2 seconds. These happen when two neutron stars collide and merge, creating what scientists politely call a highly energetic event. What they really mean is two dead star cores the size of Manhattan but weighing more than the sun slam into each other at a significant fraction of light speed, and the resulting explosion radiates more power than entire galaxies. These short bursts are bad, real bad, but they're not the ones that keep astrophysicists up at night. Now, the truly terrifying ones are the long-duration gamma-ray bursts, the ones that last anywhere from 2 seconds to several minutes, the ones caused by something called a hypernova, which is exactly what it sounds like, a supernova on steroids. Let me paint you a picture of what happens during a hypernova, because this is where cosmic horror meets physics. You start with a Wolf-Rayet star. That's a massive, dying star that's already blown off its outer layers and is burning through its final nuclear fuel like a trust fund kid in Vegas.
These stars are typically 25 to 50 times more massive than the Sun, spinning rapidly, with surface temperatures hitting 100,000 degrees Fahrenheit. They're cosmic time bombs on fast forward. When one of these monsters finally runs out of fuel, its core collapses in less than a second. The outer layers, still containing millions of Earth's worth of mass, suddenly have nowhere to go. They fall inward at about 15% of the speed of light. 15% of light speed. That's 28,000 miles per second. The entire star implodes faster than you can blink. The core compresses into a black hole or neutron star, and all that infalling material suddenly has nowhere to go. The rebound creates a supernova explosion. But in the case of a hypernova, something else happens. The collapsing core's rotation focuses the energy into two opposite jets, like a cosmic death ray emerging from the poles of the dying star. These jets, traveling at 99.995% of light speed, punch through the star's outer layers and shoot out into space as concentrated beams of gamma radiation. The photons in these beams are so energetic that a single gamma-ray photon carries about 1,000,000 times more energy than a photon of visible light. This is a gamma-ray burst. This is what happens when the universe decides to flex. Now you might be thinking, okay, cool light show, but these things happen in distant galaxies, right? We're safe? Oh, you sweet, naive soul. The thing about gamma-ray bursts is that they're directional. The energy doesn't spread out in all directions like a normal supernova. It's focused into narrow jets, usually only a few degrees wide. Think of it like the difference between a light bulb and a laser pointer. A light bulb illumines a room. A laser pointer can blind you from across a parking lot. Gamma-ray bursts are laser pointers fired by dying stars, and they can blind you from across the galaxy. In 2004, a gamma-ray burst from a magnetar, a type of neutron star with an absurdly powerful magnetic field, hit Earth. Now, before you panic, this magnetar was 50,000 light-years away, which in cosmic terms is practically next door. And the burst wasn't even aimed directly at us, we just caught the edge of it. You know what happened? It disrupted Earth's ionosphere. It affected radio communications. It temporarily changed the shape of our atmosphere. From 50,000 light-years away, from a glancing blow. A direct hit from a nearby gamma-ray burst would be, well, we'll get to that. But first, let me tell you about the time we almost missed discovering these things entirely. The year was 1967. The United States was deep into the Cold War and very concerned that the Soviet Union might be secretly testing nuclear weapons in space in violation of the Partial Test Ban Treaty. So the U.S. launched a series of satellites called Vela, Spanish for Watchman, designed to detect the gamma-ray signatures of nuclear explosions. The Vela satellites did their job perfectly. They detected gamma-ray bursts all over the sky, regularly, dozens of them.
The problem was, these bursts weren't coming from Earth orbit or the Moon or anywhere nearby. They were coming from random directions in deep space. And they were far more powerful than any nuclear weapon humanity had ever built. The military kept this classified for years. They genuinely didn't know what they were seeing. Were these alien weapons? Some kind of cosmic warfare? The data made no sense. It wasn't until 1973 that the findings were declassified and published in a scientific journal. Astrophysicists looked at the data and realized we'd been watching stars die across the universe, and their death screams were so loud we could hear them with military spy satellites designed to catch nuclear bombs. Since then, we've detected thousands of gamma-ray bursts. NASA's Swift satellite catches about one per day. Most are billions of light-years away, so far that the light we're seeing left those galaxies when Earth was still a molten rock, or before life even existed here. But here's what keeps me up at night. The detection rate suggests that gamma-ray bursts happen somewhere in the observable universe roughly once per day. That's 365 stellar death rays firing into the cosmos every single year. Most point away from us. Some point toward us but are too far away to matter. But eventually, inevitably, one will be close enough and aimed right at us. And when I say close enough, I mean within 10,000 light-years. That sounds far, right? It's not. There are thousands of stars within 10,000 light-years of Earth. Our galaxy is 100,000 light-years across. 10,000 light-years is our cosmic neighborhood. Any Wolf-Rayet star, any massive binary system, any magnetar within 10,000 light-years that happens to fire a gamma-ray burst in our direction would be, to put it scientifically, very bad for us. How bad? Let me introduce you to the Ordovician extinction. 450 million years ago, Earth was doing pretty well. The oceans were full of life, trilobites, nautiloids, early fish. The continents were barren rock, but the seas were thriving. Biodiversity was exploding. And then, suddenly, about 85% of all marine species went extinct. This wasn't a slow die-off. This was fast. Geologically speaking, it happened in an instant. One era, life is thriving. Next era, most of it is dead. Scientists have debated the cause for decades. Ice age? Volcanic eruptions? Meteor impact? In 2003, a team of researchers published a paper suggesting something far more terrifying. What if Earth got hit by a gamma-ray burst? Their model showed that a 10-second burst from a hypernova 6,000 light-years away would strip away half of Earth's ozone layer in seconds. UV radiation levels would spike to lethal levels. The marine food chain would collapse as phytoplankton died en masse. The extinction pattern would match exactly what we see in the fossil record. It's a hypothesis, not proven fact, but it's disturbingly plausible. And it means that the Ordovician extinction, one of the big 5 mass extinctions in Earth's history, might have been caused by a star that died 6,000 years before the light reached us, and we never saw it coming. Think about that for a moment. A star exploded when humans were still millions of years away from existing. The gamma-ray beam traveled across the galaxy for millennia, and 450 million years ago, it finally reached Earth and killed almost everything in the ocean in a matter of weeks. No warning, no defense, just a flash of light that had been racing toward us since before dinosaurs, before plants, before anything walked on land. And when it arrived, it rewrote the story of life on Earth. Now, before you spiral into existential dread, let me give you some good news. Gamma-ray bursts are rare. The odds of one hitting Earth in any given year are astronomically small. We're talking about a lottery where the prize is extinction, and the chances are maybe 1 in a few million per year. But, and this is a critical but, that's the average odds. The real question isn't what are the odds in general. The real question is, are there any stars nearby that could produce a gamma-ray burst and are currently aimed at us? And the answer to that question is what we're going to explore next, because there is one, and it's been making scientists nervous for 2 decades. Its name is WR94, and it's staring right at us.
Before we get to the gun pointed at our head, let's talk about what happens when gamma-ray bursts actually hit something, because we've seen the aftermath, and it's not pretty. In 1997, astronomers detected GRB 970508, a gamma-ray burst so powerful that it was visible to optical telescopes for weeks after the initial burst. This was the first time we'd ever gotten a good look at the crime scene where a gamma-ray burst had occurred. What they found was sobering. The host galaxy, the galaxy where this star had exploded, showed signs of massive devastation in the regions surrounding the burst. The intense radiation had ionized huge clouds of gas, stripping electrons from atoms across thousands of light years. Any planets in the direct path of those jets? Sterilized. Utterly and completely sterilized. But here's what's truly disturbing. We've now observed gamma-ray bursts from galaxies billions of light years away. That means the light left those galaxies billions of years ago. The bursts we're detecting today are ancient history, ghosts of stellar deaths that happened when the universe was young. And we keep finding more, stronger ones, closer ones. In 2008, astronomers detected GRB 08319b, which briefly became the most distant object visible to the naked eye. For about 40 seconds, if you'd been looking at exactly the right spot in the sky with no telescope, you could have seen a flash of light from a gamma-ray burst 7.5 billion light-years away. Think about the math here. That burst was so powerful that despite the light traveling for 7.5 billion years, spreading out, weakening, redshifting, it was still bright enough to see with your naked eye. At its peak, GRB 08319b was 2.5 million times brighter than the brightest supernova ever recorded. If that burst had occurred in our galaxy, say 10,000 light-years away instead of 7.5 billion, it would have appeared brighter than the full moon. You could have read a book by its light at midnight, and everything on the day side of Earth facing that direction would have been bathed in lethal radiation. But let's bring this closer to home. Let's talk about what we've learned from studying nearby stellar candidates. Eta Carinae is one of the most massive stars in our galaxy, sitting about 7,500 light-years from Earth. It's a hypergiant, one of the most luminous stars known, so bright and massive that it's been slowly self-destructing for centuries. In the 1840s, it underwent what's called the Great Eruption, where it briefly became the second brightest star in the night sky, despite being 7,500 light-years away. Eta Carinae is a gamma-ray burst candidate. When it goes supernova, and it will, could be tomorrow, could be 100,000 years from now, there's a chance it could produce a GRB. Here's the good news. Eta Carinae's rotational axis isn't pointed at Earth. The jets, if they form, would fire off into space in directions away from us. We'd get a spectacular light show, but no extinction event. Here's the bad news. We found another star that doesn't share that convenient property. Before we get there, though, I need you to understand something about Wolf-Rayet stars, because WR04, the star we're about to discuss, is one of them, and you need to understand why these stars are so dangerous. Wolf-Rayet stars are the final evolutionary stage of the most massive stars in the universe. When a star is born with more than 25 times the mass of the Sun, it burns through its fuel absurdly fast. While our Sun will shine for 10 billion years, a massive star might only last a few million years before it runs out of hydrogen. When that happens, the star starts burning heavier elements, first helium, then carbon, then oxygen, neon, silicon, climbing up the periodic table, each stage burning faster than the last. Hydrogen fusion takes millions of years. Silicon fusion takes days. The star becomes unstable. It starts shedding its outer layers in massive stellar winds, blowing off material at speeds of up to 2,000 kilometers per second. These winds are so powerful that they strip away the star's entire outer envelope, exposing the ultra-hot core underneath. What's left is a Wolf-Rayet star, an exposed stellar core, surface temperature around 100,000 degrees, mass loss rate of 1 Earth mass per year, and a rotational speed that's off the charts. These stars are spinning so fast, they're basically self-destructing in slow motion. And when they finally die, hypernova, gamma-ray burst, the whole cosmic nightmare package. We know of about 500 Wolf-Rayet stars in our galaxy. Most are far away or oriented such that even if they explode, their jets would miss us. But there's one, just one, that has astronomers genuinely worried.
WR104 is a Wolf-Rayet star located about 8,000 light-years from Earth in the constellation Sagittarius. It's part of a binary system, meaning it's locked in orbit with a companion star. The two stars circle each other every 220 days, and as they do, the Wolf-Rayet star's stellar wind creates a spiral pattern in space that looks like a cosmic pinwheel. This pinwheel pattern is beautiful. It's also terrifying, because by studying the shape of that spiral, astronomers have been able to determine the orientation of the system's rotational axis. And here is where we get to the part that keeps astrophysicists awake at night.
WR-104's rotational axis appears to be pointed within about 16 degrees of Earth. 16 degrees. That's well within the angular width of a typical gamma-ray burst jet. Now, before you start building a bunker, let me clarify. There's debate about this. Some studies suggest the axis is pointed more like 30 to 40 degrees away from us, which would put us safely outside the kill zone. But other studies, using more recent data, confirm that 16-degree estimate. The uncomfortable truth is we don't know for sure. We can't know for sure. The geometry is hard to measure from 8,000 light-years away. What we do know is this: WR-104 is going to explode. It's not a question of if, but when. It could happen tomorrow. It could happen 100,000 years from now. In cosmic terms, these are both any minute now. And when it explodes, if the jets are pointed our way, the gamma rays will travel toward Earth at light speed. There will be no warning. The light from the explosion will arrive at the exact same time as the gamma rays because they both travel at light speed. We'd detect the burst the same instant it started killing us. Let me put this in perspective. Imagine someone 8,000 miles away fires a gun at you, and the bullet travels so fast that you see the muzzle flash at the exact moment the bullet hits you. No time to duck, no time to react, just simultaneous detection and impact. That's a gamma-ray burst. That's WR-104. Oh, and here's the extra fun part. If WR-104 exploded 7,950 years ago, the gamma rays are 50 years away from hitting Earth, and we have absolutely no idea. We're sitting here talking about this threat, and the extinction-level radiation could be crossing the Orion Arm right now, 50 light-years out, racing toward us at 186,000 miles per second. If it fired 7,990 years ago, we have 10 years. If it fired 7,999 years ago, we have 1 year. We don't know. This is what makes gamma-ray bursts uniquely terrifying. With asteroids, we can track them. With solar storms, we get warnings. With supernovas, we'd see the star brightening in the months or years beforehand. But gamma-ray bursts? The first sign that WR-104 has exploded will be the gamma rays cooking our atmosphere. Now let's talk probability for a moment, because I can feel some of you reaching for the math to reassure yourselves. The odds that WR-104 is oriented perfectly to hit us are low, maybe 10 to 20% based on current estimates. The odds that it explodes in the next century are also low, maybe 1% or less. The odds that it produces a gamma-ray burst at all, rather than just a normal supernova, are maybe 50-50. Multiply those probabilities together, and you get something like a 0.01% to 0.1% chance of Earth getting hit by a WR-104 gamma-ray burst in the next 100 years. Those are good odds. You can sleep soundly knowing you'll probably never have to worry about this, right? Except, here's the thing about low-probability, high-consequence events. The risk is small, but the consequence is total. When you're talking about extinction-level threats, even a 0.1% chance is 0.1% too high. And WR-104 isn't the only candidate. It's just the one we know about that might be aimed at us. There are 500 Wolf-Rayet stars in our galaxy. There are binary neutron systems we haven't found yet. There are magnetars capable of producing SGR flares, soft gamma repeater events, that could disrupt our atmosphere from halfway across the galaxy. We've cataloged maybe 10% of the threats. The rest are out there, ticking away, and we have no idea which ones have our name on them. But let's assume the worst. Let's say WR-104 explodes tomorrow. The jets are pointed at us, and the gamma rays arrive. What actually happens? What does a gamma-ray burst do to a planet? That's what we need to talk about next, because the nightmare isn't just the initial burst, it's what comes after.
Let's walk through this scenario step by step, because I want you to understand exactly what happens when a gamma-ray burst hits Earth. And I want you to understand why it's not the quick death you might be hoping for. It's 2 p.m. on a Tuesday.
You're at work, or home, or wherever. The sky is clear. WR-104, sitting 8,000 light-years away in Sagittarius, has just collapsed into a black hole. The jets have punched through the star's outer layers and are now screaming across the galaxy at 99.995% the speed of light. The gamma-ray beam is narrow, maybe 5 degrees wide, but after traveling 8,000 light-years, even that narrow beam has spread out enough to engulf Earth and everything in our solar system. You have no idea this is happening. Nobody does. The last time anyone looked at WR-104 through a telescope, it was fine. Just another star doing star things. 8,000 years later, which is to say 10 seconds from now, the gamma rays arrive. Let me tell you what happens in those 10 seconds. At 2 p.m. and 0 seconds, orbital satellites detect an extraordinary spike in gamma radiation. Alarms go off at NASA, ESA, and space agencies worldwide. Scientists scramble to check their instruments, thinking there must be a malfunction. At 2 p.m. and 1 second, the gamma rays hit Earth's upper atmosphere. Each photon carries about 1,000,000 times more energy than a photon of visible light. They slam into atoms in the stratosphere and ionosphere, stripping electrons and creating cascades of secondary particles. At 2 p.m. and 2 seconds, Earth's magnetic field, which normally protects us from solar wind and cosmic rays, does exactly nothing. Gamma rays don't care about magnetic fields. They punch straight through. At 2 p.m. and 3 seconds, the ozone layer begins to disintegrate. Ozone molecules, O3, are ripped apart by the intense radiation. Chemical reactions that normally take years to deplete ozone are happening across the entire planet in real time. At 2 p.m. and 4 seconds, people start noticing something weird. The sky is shimmering, changing color. If you're on the day side of Earth facing the burst, you might see a flash of blue-white light. It's beautiful, actually. It's also the last beautiful thing you'll ever see. At 2 p.m. and 5 seconds, anyone outside on the dayside hemisphere starts feeling it, a tingling sensation on exposed skin. Not painful yet, just strange, like standing too close to a microwave. At 2 p.m. and 6 seconds, 50% of Earth's ozone layer is gone. Ultraviolet radiation from the sun, which is normally blocked by ozone, starts flooding through. But this is insignificant compared to the UV being created by the gamma-ray burst itself, as it ionizes the atmosphere. At 2 p.m. and 7 seconds, electronics start failing. Satellites are getting fried. Power grids are experiencing massive surges. The ionosphere is so disrupted that radio communications worldwide go dead. At 2 p.m. and 8 seconds, the ozone depletion reaches 70%. The sky is now visibly orange-brown as nitrogen dioxide, created by the gamma rays splitting nitrogen molecules, fills the upper atmosphere. This is the same gas that makes smog brown. Now the entire planet is wrapped in it. At 2 p.m. and 9 seconds, UV radiation levels on the surface are reaching 1,000 times normal. Anyone outside without protection is getting third-degree burns on exposed skin. Eyes are being damaged. But most people are still confused, not panicking, not yet. This all happened too fast. At 2 p.m. and 10 seconds, the gamma-ray burst ends. WR-104, 8,000 light-years away, has finished its 10-second death scream. The jets shut off as abruptly as they started. But the damage has only just begun. Within an hour, people on the day side are flooding hospitals with radiation burns, eye damage, and UV exposure. Anyone who was outside is in trouble. Anyone who looked at the sky during those 10 seconds is now blind. Within 6 hours, global communications are crippled. Satellites are dead or dying. GPS is offline. Weather satellites are gone. The internet backbone, which relies on satellite connections for international traffic, is fractured. Within 24 hours, scientists have confirmed what happened and delivered the news: Earth has been hit by a gamma-ray burst. The ozone layer is mostly destroyed, UV radiation levels are at extinction-level intensities, and will remain that way for at least 5 years, the time it takes for the ozone layer to regenerate. But here's the problem. The ozone layer can only regenerate if we still have oxygen-producing life to create ozone, and we're about to lose most of that. Let me explain what happens next, because this is where the real extinction begins. Phytoplankton, microscopic algae and bacteria that live in the top 200 meters of the ocean, are responsible for producing about 50 to 80% of Earth's oxygen. They also form the base of the marine food chain. Everything in the ocean, from sardines to whales, ultimately depends on phytoplankton. Phytoplankton live in the top 200 meters of the ocean, where sunlight penetrates. They need light to photosynthesize, but they're also incredibly vulnerable to UV radiation. Under normal conditions, the ozone layer blocks most UVB and UVC radiation. With the ozone layer gone, phytoplankton start dying en masse. Within a week, satellite observations, well, the few satellites still working, show massive algae die-offs across the world's oceans. The ocean's surface, normally teeming with microscopic life, is turning into a dead zone. Within 2 weeks, the marine food chain starts collapsing. Small fish and zooplankton that feed on phytoplankton are starving. Larger fish that feed on small fish follow. Dolphins, seals, and whales all suffering from the same problem. The ocean is dying from the bottom up. But it's not just the ocean. On land, plants are struggling. UV radiation at 1,000 times normal levels is damaging plant DNA, disrupting photosynthesis, and causing widespread die-offs of crops and natural vegetation. Trees can survive for a while, they have bark to protect them, but grasses, shrubs, and most agricultural crops are toast. Within a month, global food supplies are in free fall. Crops are failing, livestock are dying, not just from lack of food, but from UV exposure and the collapse of the feed supply. Fishing is pointless, the ocean is a graveyard. Within 3 months, even if you're rich enough to afford the astronomical prices for what little food remains, you're facing another problem: nutritional collapse. The global supply chain, which depends on international shipping, satellites for navigation, and stable power grids, has crumbled. Food isn't moving from producers to consumers. And here's where the social collapse accelerates. Governments declare emergencies, martial law, food rationing. But it's too little too late. Cities start emptying as people flee to rural areas, hoping to grow their own food. But there's a problem. You can't grow food outside. The UV radiation will kill the crops. You need greenhouses with UV filtering glass. Most people don't have that. Within 6 months, famine is global. Not food is expensive famine, real catastrophic biblical famine. The kind where people are dying by the millions. The kind where social order breaks down completely.
The global death toll within the first year would be somewhere between 2 and 4 billion people. Not from the gamma ray burst itself. Remember, that only lasted 10 seconds, and most people were indoors. But from the cascading consequences: starvation, disease, violence over dwindling resources. Within 2 years, even the survivalists are in trouble. Those underground bunkers and stored food supplies, they're running out. You can't grow food underground without artificial light, and power grids are still fractured. Solar panels don't work well when the atmosphere is still thick with nitrogen dioxide aerosols. Within 3 years, the ozone layer has partially recovered, but it doesn't matter. The damage is done. The population has crashed from 8 billion to maybe 2 to 3 billion. Entire regions are depopulated. Civilization as we know it is gone. And the darkest part? This is the optimistic scenario. This assumes the gamma ray burst was relatively weak and lasted only 10 seconds. If it lasted longer, say 30 seconds, the ozone depletion would be near total. If it was from a closer source, say 2,000 light-years instead of 8,000, the intensity would be 16 times higher. In a worst-case scenario, a nearby, long-duration burst from less than 3,000 light-years away, the UV radiation would be so intense that it would sterilize the land surface completely. Anything exposed to the sky would die. Oceans would become dead zones. The only survivors would be deep-sea organisms and things living underground.
We're talking about reducing Earth's biodiversity by 95% or more, a mass extinction on par with the Permian Triassic event, the Great Dying 252 million years ago, when volcanic activity nearly ended all complex life on Earth. Except this time, it wouldn't be volcanoes, it would be a star that died when humans were still hunting mammoths, and the death ray finally arrived in the 21st century. Now, here's the part that should really keep you up at night. We have no defense against this. None. Let me run through the options so you understand why. Can we deflect it? No. It's light. You can't deflect light. It doesn't have mass. It can't be pushed or redirected. Can we block it? Not really. You'd need a shield in space, positioned between Earth and the incoming radiation, large enough to cast a shadow over the entire planet. Even if we had the technology to build such a thing, which we don't, we'd need years of warning to position it. We don't get years, we get 0 seconds. Can we hide underground? Sure, if you've got a fully stocked underground facility with years of food, water, air recycling, and artificial grow lights. Most people don't, and even if they did, you'd emerge years later to a planet with a devastated biosphere and no functioning infrastructure. Can we evacuate to Mars or the Moon? Absolutely not. We don't have the rockets, the life support, or the infrastructure to move even 1 million people off-planet, let alone billions. And even if we did, Mars and the Moon would be hit by the same gamma-ray burst. The entire solar system is in the beam. Can we do anything? No. The answer is no. There is no planetary defense against gamma-ray bursts. You can't shoot them down, can't hide from them, can't negotiate with them. You just take the hit and hope your species survives the aftermath. And this brings me to the most absurd part of this whole situation, the economics. The global economy is worth about $100 trillion in annual GDP. Total world wealth, all the assets, property, investments, everything, is estimated at around $450 trillion. A gamma-ray burst would erase all of it instantly, not damage it, not reduce it, erase it. Because when 99% of humanity dies over 3 years, your stocks, bonds, and real estate don't matter anymore. So what's the insurance premium on that risk? What do we spend to prevent or prepare for gamma-ray bursts? The answer is, functionally, nothing. NASA's planetary defense budget is about $330 million per year. That's for asteroids. For gamma-ray bursts, 0. ESA's Space Situational Awareness budget, focused on debris and solar storms, 0 for gamma-ray bursts. Private sector investment in GRB defense, literally 0, because there's nothing to invest in. You can't defend against light-speed death rays. Let me put that in perspective. We spend $330 million a year to prevent asteroid impacts, a threat that might kill millions if we're unlucky. We spend $0 to study or prepare for gamma-ray bursts, a threat that would kill billions and end civilization as we know it. Why? Because asteroids are preventable. We can see them coming, we can potentially deflect them, and thus there's value in spending money on the problem. Gamma-ray bursts are not preventable. They can't be stopped. So from a cynical economics perspective, why spend money on research when there's nothing you can do with that research? It's the most rational, irrational decision humanity has ever made. We're sitting on a planet in a galaxy with a loaded gun pointed at us, and we've collectively decided that since we can't dodge the bullet, we might as well not think about it. The official policy on gamma-ray bursts is essentially hope for the best, and if it happens, well, it was nice knowing you. Sleep tight.
All right, let's take a step back from the nightmare scenario and talk about the math. Because I know some of you are doing calculations in your head, trying to figure out if you should be panicking right now. Spoiler, you probably shouldn't be panicking. But you also shouldn't be sleeping soundly. Let me break down the actual odds of Earth getting hit by a gamma-ray burst, because the picture is both reassuring and disturbing depending on how you look at it.
First, the reassuring part. Space is really, really big, like absurdly big. The Milky Way galaxy is about 100,000 light-years across and contains somewhere between 100 and 400 billion stars. Even with 500 known Wolf-Rayet stars, potential gamma-ray burst progenitors, the odds that any single one of them is aimed directly at Earth are low. A typical gamma-ray burst jet is about 2 to 10 degrees wide. For reference, your clenched fist at arm's length covers about 10 degrees of sky. So we're talking about very narrow beams. The odds that a random star's rotational axis is aligned with Earth are roughly 1 in 50 to 1 in 500, depending on the jet width. Now, multiply that by the odds that a given Wolf-Rayet star will explode in, say, the next 100,000 years. For most Wolf-Rayet stars, that probability is somewhere between 1% and 10%. Multiply those together, and you get very small numbers. For any individual star, the odds of it producing a gamma-ray burst that hits Earth in your lifetime are less than 0.001%. So why are we even talking about this? Because there are 500 known Wolf-Rayet stars and hundreds of thousands of other massive stars that could potentially produce gamma-ray bursts, and millions of binary neutron star systems that could merge and fire off short-duration bursts, and we've only cataloged a tiny fraction of them. When you're playing the lottery with millions of tickets, even if each individual ticket has a 1 in a million chance, eventually somebody wins. Or, in this case, eventually somebody loses catastrophically. Studies have estimated that Earth experiences a nearby, within 10,000 light-years, gamma-ray burst roughly once every 15 million years on average. That sounds comforting, until you realize the last one might have happened 450 million years ago, the Ordovician extinction, which means we're not due for another one for a long time. Or it means we're overdue. Statistics don't care about fairness. But let's focus on WR104 specifically, since that's the star we know is potentially aimed at us. WR104 is 8,000 light-years away. That's close enough to be a threat if it produces a powerful burst, but far enough that we're not in the immediate kill zone. Scientists estimate that a GRB from 8,000 light-years would deplete about 50 to 70% of Earth's ozone layer if it hit directly. That's catastrophic, but it's not the near-total sterilization you'd get from a burst at 2,000 light-years. The star's rotational axis, remember that's what determines which direction the jets will fire, is estimated to be somewhere between 16 and 40 degrees off from Earth. If it's 16 degrees, we're in trouble. If it's 40 degrees, we're fine. We don't know which number is correct. The measurements are difficult and depend on modeling the binary system's orbital mechanics, which requires assumptions about the companion star's mass, the orbital inclination, and other factors we can't measure precisely from 8,000 light-years. Some astronomers say we're worrying over nothing. Others say we should be monitoring WR104 constantly, just in case. The truth is, we're in a state of cosmic uncertainty. It's like living in a house where there might be a gas leak. You're probably fine, but wouldn't it be nice to know for sure? Except we can't know for sure, and even if we could confirm that WR104's axis is pointed directly at us, what would we do with that information? Panic? Build bunkers? Pray? There's literally nothing actionable we could do with the knowledge, which is why most people don't spend their days worrying about it. It's the ultimate unfixable problem. But let's talk about other candidates, because WR104 is just the one we know about. Eta Carina, which I mentioned earlier, is another major candidate. It's 7,500 light-years away and is one of the most massive stars in the galaxy. If it explodes, and when I say if, I mean when, possibly tomorrow, it could produce a gamma-ray burst. The good news, Eta Carina's rotational axis is estimated to be about 45 degrees away from Earth. We'd see an incredible light show, but we'd avoid the death ray. The bad news, there are probably dozens of other massive stars within 10,000 light-years that we haven't fully characterized yet. Some of them could be oriented towards us, and we just don't know yet. Ik Pegasi is another interesting case. It's a binary system containing a white dwarf and a main sequence star only 150 light-years away. When the main sequence star eventually expands and starts feeding mass to the white dwarf could explode as a Type 1a supernova. Now, Type 1a supernovae don't typically produce gamma-ray bursts, but IK Pegasi is so close that even a normal supernova would be problematic. The good news is this event is millions of years away, and by the time it happens, the system will have moved out of our neighborhood due to stellar proper motion. But here's the unsettling part. We keep discovering new threats. In 2016, astronomers found a star called Epip, named after the Egyptian serpent god of chaos, which is a Wolf-Rayet binary about 8,000 light-years away. And guess what? It shows evidence of producing a dust pinwheel just like WR104. The system might be pointed at us. We don't know yet. Every few years, we find another potential candidate. The list grows, not shrinks. And each new discovery is a reminder that our galactic neighborhood is more dangerous than we thought. Now let's talk about the things that aren't stars, but might be even worse. Magnetars. Magnetars are neutron stars with magnetic fields so intense they defy comprehension. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. A magnetar has a magnetic field 1,000 times stronger than that. These magnetic fields are so powerful that they warp the vacuum of space itself. If you stood 1,000 kilometers from a magnetar, the magnetic field would rip the atoms in your body apart by pulling on the electrons harder than the electromagnetic force can hold atoms together. Magnetars occasionally have temper tantrums called starquakes. The crust of the neutron star, made of crystallized nuclear matter, cracks under the stress of the immense magnetic field. When that happens, the magnetic field lines snap and reconnect, releasing a burst of gamma rays called an SGR flare, short for soft gamma repeater. Soft is relative. These bursts are still incredibly powerful. On December 27, 2004, a magnetar called SGR 1806-20, located 50,000 light-years away on the other side of the galaxy, had a starquake. The resulting SGR flare released more energy in 1/10 of a second than the Sun emits in 150,000 years. The gamma rays and X-rays from that flare hit Earth 10 seconds after the neutron star cracked, and despite being 50,000 light-years away, halfway across the galaxy, the radiation was powerful enough to ionize Earth's upper atmosphere, disrupt radio communications, and temporarily blind several spacecraft. From 50,000 light-years away. If that same event had occurred from 10,000 light-years away, the intensity would have been 25 times higher. From 1,000 light-years away, 2,500 times higher. An SGR flare from a nearby magnetar could cause ozone depletion comparable to a gamma-ray burst. And here's the fun part. We know of about 30 magnetars in the Milky Way. There are probably hundreds more we haven't detected yet. And we have no way of predicting when they'll have starquakes. So, in addition to worrying about massive stars exploding and firing death rays at us, we also have to worry about neutron stars having bad days and accidentally irradiating the neighborhood. The universe is not a safe place. But let's zoom out even further, because there's an even more disturbing question we need to address. How many civilizations have been wiped out by gamma-ray bursts? Think about it. If gamma-ray bursts happen regularly in galaxies, and if they can sterilize planets from thousands of light-years away, how many alien civilizations might have been erased by cosmic bad luck? This is sometimes called the gamma-ray burst hypothesis for the Fermi paradox. Enrico Fermi famously asked, "Where is everybody?" If the universe is billions of years old and contains billions of galaxies, each with billions of stars, where are all the aliens? One answer might be they got unlucky. Imagine an alien civilization on a planet 5,000 light-years from a Wolf-Rayet star. They've developed technology, built cities, maybe even achieved interstellar travel. They're thriving. And then, one day, without warning, a gamma-ray burst from that Wolf-Rayet star wipes them out. Not because they did anything wrong, not because they failed to prepare, just because a star happened to explode and happened to be aimed at them. From our perspective, watching from billions of light years away, we'd never know they existed. We'd see the gamma-ray burst, we'd study the physics, and we'd move on. We wouldn't see the extinct civilization that the burst left behind. How many times has this happened? How many intelligent species have been erased by gamma-ray bursts before they could leave any mark on the universe? We don't know. We can't know. But statistically, if the universe has been producing civilizations for billions of years and gamma-ray bursts happen regularly, the odds are good that countless civilizations have been destroyed this way. It's a sobering thought. Life is rare, intelligence is rarer, and the universe is actively hostile to both. Gamma-ray bursts are just one of many ways the cosmos can kill you without warning. But here's the worst part. We might never even know we're about to die. If WR-104 exploded 7,000 years ago, the gamma rays are 1,000 years away. If it exploded 7,900 years ago, the gamma rays are 100 years away. If it exploded 7,990 years ago, the gamma rays are 10 years away. We have no way of knowing. The light from the explosion arrives at the same time as the gamma rays. There is no advance warning. The first sign that WR-104 has exploded will be the gamma ray burst hitting our atmosphere. You could be watching that star through a telescope, and it would look perfectly normal, right up until the moment it kills you. That's the unique horror of light-speed threats. With an asteroid, you can see it coming months or years in advance. With a solar storm, you get hours or days. With a supernova, you'd see the star brightening in the lead-up to the explosion. But with gamma-ray bursts, the warning time is 0. You don't get a chance to say goodbye, to make peace, to finish your bucket list. You just die. And then everyone else dies over the next few years as the biosphere collapses. And the absolute darkest timeline? It might have already happened. WR-104 might have exploded centuries ago, and the gamma-ray beam is crossing the galaxy right now, getting closer every second. In 50 years, or 5 years, or 5 months, it will reach Earth. And when it does, we'll have 10 seconds to realize that the star we'd been nervously watching for decades had already killed us before we even knew to worry about it. Sleep tight.
So, where does that leave us? We've established that gamma-ray bursts are real, they're deadly, they're unpredictable, and there's nothing we can do to stop them. We've identified at least one star, WR-104, that might be aimed at us and could fire at any moment. We've calculated the odds and found them disturbingly non-zero. What now? The honest answer is, we wait, we watch, we hope for the best, because that's literally all we can do. But let's talk about what we're actually doing or not doing to monitor these threats, because the situation is somehow both impressive and depressing. On the impressive side, we have an entire network of satellites dedicated to detecting gamma-ray bursts. Fermi Gamma-Ray Space Telescope, launched in 2008, detects about 1 gamma-ray burst per day. SWIFT, launched in 2004, can reorient itself within seconds of detecting a burst to capture optical and X-ray images of the afterglow. These satellites are incredible pieces of technology. They can pinpoint the location of a gamma-ray burst within a few arc seconds, allowing ground-based telescopes to immediately start observing the host galaxy. We've learned more about gamma-ray bursts in the last 20 years than in the previous 50. We now know that long-duration bursts come from collapsing massive stars. We know that short-duration bursts come from neutron-star mergers. We can measure the energy spectrum of the gamma rays and use that to estimate the distance to the burst. We're building detailed models of the physics involved. It's genuinely impressive science, and it's completely useless for protecting Earth. Because here's the thing. Detecting gamma-ray bursts after they happen is great for astronomy. It's terrible for planetary defense. By the time Fermi or Swift detects a burst, the gamma rays have already hit us. There's no warning, no alert system, no evacuation plan, just observation and post-mortem analysis. It's like having a state-of-the-art autopsy lab, but no doctors. We're very good at figuring out what killed us after we're dead. Now, you might ask, couldn't we build a system to detect the precursor signs of a gamma-ray burst before it fires? The answer is maybe, but it wouldn't help much. Here's why. The precursor to a long-duration gamma-ray burst is a hypernova, a massive star collapsing into a black hole. And the time between the collapse starting and the gamma-ray jets firing is measured in seconds. Even if we had a telescope powerful enough to detect the collapse in real time, which we don't, we'd have maybe 10 seconds of warning before the burst reached us. 10 seconds is not enough time to do anything except maybe send out a tweet that says, "We're all about to die, here's why." And remember, this is only for bursts happening in our galaxy. For bursts from other galaxies, we wouldn't see any precursor at all. The burst would be long over by the time the light reached us. So detection isn't really the solution. What about prevention? Well, here's where it gets darkly comedic. You can't prevent a star from exploding. You can't redirect a gamma-ray beam. You can't shield a planet from light-speed radiation. The laws of physics don't care about our survival instincts. The only prevention would be to somehow destroy the star before it explodes naturally. And setting aside the absurd ethics of preemptively destroying a star, potentially killing any life in that system, we don't have the technology to do it. You'd need to deliver enough energy to disperse a star that's 25 times more massive than the Sun. We can't even deflect asteroids reliably yet. So prevention is off the table. Detection doesn't help. What about mitigation? This is where things get slightly less hopeless, but only slightly. If we knew a gamma-ray burst was coming, say if we somehow detected the precursor with 10 seconds of warning, we could potentially shut down power grids to prevent damage to transformers. We could alert people to get indoors to avoid UV exposure. We could put satellites into safe mode. But 10 seconds isn't enough time to do most of that. You can't shut down a continental power grid in 10 seconds. You can't alert 8 billion people to take cover. You can't coordinate a global response when the warning comes 10 seconds before impact. The only realistic mitigation is long-term preparation, building underground shelters with years of supplies, developing closed-loop life support systems, creating seed banks and genetic repositories to preserve Earth's biodiversity in case we need to rebuild the biosphere. Oh wait, we're already doing some of that. Not because of gamma-ray bursts, but because of nuclear war, climate change, and asteroid impacts. So at least if a gamma-ray burst hits, we'll have some infrastructure in place for the survivors. The Svalbard Global Seed Vault in Norway contains samples of nearly 1 million crop varieties, stored in a frozen mountain bunker. It's designed to survive nuclear war, asteroid impacts, and climate catastrophe. It would also survive a gamma-ray burst, since it's underground and shielded. Several countries have underground bunkers designed to protect government leadership in case of nuclear war. These would also provide protection from gamma-ray bursts, at least for the initial event and immediate aftermath. SpaceX and other companies are working on making humanity multiplanetary, with Mars as the eventual goal. If we had a self-sustaining colony on Mars, then a gamma-ray burst hitting Earth wouldn't end humanity. We'd survive on Mars and could potentially recolonize Earth once the biosphere recovered. So there's hope, in a dark, survivalist kind of way. If a gamma-ray burst hit tomorrow, some humans would probably survive. Maybe a few thousand, maybe a few million if we're lucky. And over thousands of years, we could potentially rebuild. But let's be honest, that's not a plan. That's a Hail Mary. That's hoping the species gets lucky and that the survivors have the resources, knowledge, and will to rebuild civilization from the ashes.
The rational thing to do would be to invest heavily in becoming multiplanetary as quickly as possible. Spread humanity across multiple worlds so that no single cosmic disaster can wipe us all out at once. It's the ultimate backup plan. But we're not doing that rationally. We're doing it slowly, cautiously, driven more by commercial interests and national pride than by existential risk mitigation, which means that right now, today, humanity remains vulnerable to single-point failures. One gamma-ray burst, one planet, one species. If we lose the roll of the cosmic dice, that's it. Game over. The universe moves on without us. Now, let me address something that I'm sure some of you are thinking. If gamma-ray bursts are so dangerous, and if they happen regularly in the universe, why hasn't one wiped us out already? We've been around for 200,000 years as a species, and millions of years before that as hominids. Surely, if the risk was that high, we'd already be dead. That's actually a good point, and it's called the anthropic principle in philosophy. The argument goes like this. We can only observe a universe where we exist. Therefore, we must live in a universe, or a region of the galaxy, where gamma-ray bursts are rare enough that intelligent life can evolve. If gamma-ray bursts happened every million years in our neighborhood, complex life would never have had time to develop. The fact that we're here, pondering this question, is evidence that we live in a relatively safe region of the galaxy, where mass extinction events are rare. But rare doesn't mean impossible. It just means the odds are good in any given century, millennium, or million-year span. But over long enough timescales, rare events become inevitable. Earth has been around for 4.5 billion years. Complex life has been around for about 600 million years. In that time, we've had 5 major mass extinctions and dozens of smaller ones. Some were caused by asteroid impacts, some by volcanic eruptions, one, possibly, by a gamma-ray burst. The pattern suggests that extinction-level events happen roughly every 100 million years on average. We're about 65 million years out from the last one, the asteroid that killed the dinosaurs. By that logic, we've got another 35 million years before the next one is due. But that's just an average. It could happen tomorrow. It could happen in a billion years. Statistics don't care about our sense of fairness or timing. And here's the really unsettling part. If a gamma-ray burst hit Earth tomorrow and wiped out 99.9% of all life, the universe wouldn't notice. There'd be no cosmic justice, no monument to our achievements, no record of humanity's brief existence. In a few million years, the biosphere would recover. New species would evolve. Maybe intelligence would evolve again. Maybe those future intelligent creatures would dig up our fossils and wonder what wiped out this ancient civilization that briefly appeared and then vanished. Or maybe they wouldn't. Maybe Earth would remain a barren rock for billions of years until the sun expands into a red giant and swallows it whole. Either way, the universe doesn't care. Gamma-ray bursts will keep happening, stars will keep exploding, and life, wherever it arises, will remain vulnerable to cosmic bad luck. This is the reality of living in a universe governed by physics rather than purpose. Bad things happen to good civilizations not because they deserve it, but because they were in the wrong place at the wrong time and a star 8,000 light-years away had a bad day. So what's the takeaway here? What should you personally do with this information? Honestly, probably nothing. The odds that a gamma-ray burst will hit Earth in your lifetime are vanishingly small. You're far more likely to die in a car accident, from heart disease, from climate change, or from any number of mundane threats that we actually can do something about. Worrying about gamma-ray bursts is like worrying about being struck by lightning while simultaneously being bitten by a shark and winning the lottery. It could happen, technically, but it's not worth losing sleep over. But, and this is important, just because something is unlikely doesn't mean we should ignore it entirely. Low-probability, high-consequence events deserve attention, even if that attention is just acknowledging they exist and making sure we're doing what little we can to prepare. Supporting space agencies like NASA and ESA, which monitor the sky for threats. Supporting efforts to make humanity multiplanetary, so we're not all living on one fragile world. Supporting science education, so future generations understand these risks and can develop better solutions than we have. These are things you can do that don't require paranoia or bunker building, just basic support for the idea that humanity should be paying attention to existential risks, even the ones we can't prevent. And maybe, just maybe, check on WR104 once in a while. Not obsessively, not anxiously, just keep an eye on it. Make sure it's still there, still quietly burning away in Sagittarius, not yet collapsing into a black hole. Because the day we look at WR104 and it's not there anymore, we'll have about 10 seconds to appreciate the irony that we spent all this time worrying about it and it still caught us by surprise. So here's my final thought. Gamma ray bursts are a reminder of something important. We live in a universe that is beautiful, vast, and utterly indifferent to our survival. The cosmos doesn't hate us, but it doesn't love us either. It just is. And sometimes, is includes extinction-level death rays firing randomly across the galaxy. The fact that we're here, talking about this, is a miracle of cosmic luck. We're alive in an era where gamma-ray bursts is something we can detect and study, rather than just dying from without ever understanding what killed us. We're alive at a time when we can, potentially, do something about it by spreading to other worlds. We're living in the brief window between ignorance and extinction, and we have a choice about how to use that time. We can spend it worrying about WR104 and checking the sky every night for signs of doom, or we can spend it building, creating, exploring, and pushing the boundaries of what humanity can achieve. We can accept that, yes, we live in a dangerous universe, and yes, we might get unlucky someday. But until that day comes, if it ever comes, we might as well make the most of the time we have. Because the alternative is spending your life afraid of a threat you can't control, and that's no way to live. The universe is vast and dangerous, but it's also spectacular and worth experiencing. Gamma-ray bursts will happen whether we worry about them or not. Stars will explode, jets will fire, and somewhere, somehow, life will find a way to continue. Unless WR104 exploded 7,900 years ago, in which case the gamma rays are about a year out and we're all spectacularly screwed. But probably not. Probably we're fine. Probably you'll finish watching this video, go about your day, and never think about gamma ray bursts again. And that's okay. That's healthy even. Because the point of understanding existential threats isn't to live in fear, it's to appreciate the improbable gift of existence in a universe that didn't have to let us exist at all. So go outside, look up at the stars, appreciate that you're alive right now in a galaxy that hasn't killed you yet. Marvel at the fact that you're made of stardust, living on a rock orbiting a nuclear furnace, protected by a magnetic field and an atmosphere that, so far, have done their job of keeping you alive. And if one day a flash of light appears in the sky and you feel a strange tingling on your skin, well, at least you'll know what it is. At least you'll have 10 seconds to appreciate the cosmic coincidence that brought you into existence and the cosmic coincidence that's about to end it. And honestly, in a universe as vast and uncaring as ours, that's almost poetic.